Welcome to the presentation of Siglent Technologies. My name is Thomas Rottach and I'm working in the Sales and Marketing department. Here we see today's agenda. In the first part we will try to explain where the growing demand for power electronics come from. The second part will have a quick look on the power conversion topic, which then leads automatically to the design challenges and why it is needed to do extensive testing. In the last part, we will have a look at selected test scenarios and an overview about additional tests. Let's have a look at the trends which we currently see on the market. So the electrification of transportation, this not only affects cars, buses and trucks, but it also affects the transport of goods. Maybe here what we see with the drone, so delivering the packets by drone in the rural area to avoid the driver have to go far outside the city. Or maybe the transport of persons in volocopters is another topic which is currently under development. The autonomous driving is also related to the electrification. It's the way of moving people without interaction. So this is very important for reliable electronics, and therefore it's also affecting the power market. On the other hand, we have the renewable energy. We all know the global warming is ongoing, and on the opposite side, we have trends like electrification of transportation, where we need more electrical power, and this is also increasing process. And on the opposite side, we need to be able to generate electrical energy in a proper way without affecting the environment too much. So there is also still a lot of development ongoing. Last but not least, the digitization. We all have heard about a smart factory, smart cities, smart home. This is also not obvious in the first part, but it's also affecting the power electronics market. Here we have again the digitization. I'm trying to give an idea how the digitization affecting the power electronics. So what we see is a continuously growing number of battery powered devices, and therefore it is needed to have high efficient converters, power converters, DC-DC converters, so that there is less energy wasted and the battery lasts as long as possible. And the second part is also related to IoT in this case. 5G autonomous driving will also grow the amount of data, and somewhere in the backbone this huge amount of data from streaming videos, from surfing in the web, also the data reporting of the sensors somehow needs to be handled. And therefore we see a fast growing number of data centers, and in the data centers we have all the servers, and all the servers needs energy, and there are many power converters involved here. And as more efficient the power converters in the data centers are, of course the better it is, because you have less heat dissipation. And one of the biggest part of electrical energy which are consumed from data centers is the amount for air conditioning, because of getting rid of the heat dissipation from the converters. So in this case you can save with higher efficiency in the conversion. You can also save energy on the opposite side, right? Because you need less cooling. And this all together needs a growing need for electrical power. The electrification itself, of course, we see the power converters, all the motor drivers, this is also fast increasing numbers driven by electrification, and more growing need of electrical power is the result of it. And these together, so the growing need for electrical power, also pushes the extension of renewable power generation, because on one hand you are moving into the digital world, you're going more into electrical driving, electrical cars, and somehow the energy needs to come from. And as we don't want to pollute the environment with burning whatever coal or gas, so there is a strong need to go into or to make renewable energy more efficient and more available. Let's have a look at the requirements for converters. The growing need for electrical power is the driver for the below shown 4 main requirements, I would say. So, mentioned this before several times. Main goal is to achieve a higher efficiency, or at least highest possible efficiency. But higher efficiency also impacts the costs and the weight. So just imagine you have a power converter which has higher efficiency. On the opposite side, this means it has less heat dissipation. Less heat dissipation means you need to spend less money for cooling or a smaller heatsink. A smaller heatsink itself, of course, is lighter than a big one. And so you have a combination of these 3 topics already. Maybe also if you have a smaller heatsink, you also reduce the size of the device. This also is affected by it. On the opposite side, if you have a reduced size, this typically affects that you have a battery powered device. Typically these devices have to be cheap because they are mass products. The efficiency should be as high as possible because the battery mostly can't be changed, or there is at least the wish that the battery should not be changed within the next 5 years. So this is also affecting each other. The power conversion can be seen as the heart of the power electronics design. There are several ways to convert voltage or current from, for example, AC to DC, but the most common used one is the switch mode design. This is widely used because it has several advantages. So first of all, it is flexible in use. So with the setup of switching, you can generate DC voltages out of AC voltages, or you can do the same vice versa. You can also combine AC DC DC AC converters to generate AC AC converters, as well as you can achieve DC DC conversion with even up or down converting. Another important advantage is the high efficiency, which is above 80%, and with this it is much higher than from linear regulators, which are typically between 50 and 70% in the maximum range. Additionally, they are low in cost and can also be small in size. On the lower part of the slide we see a DC-DC down converter, and on the right side you see how the 2 semiconductor switches are acted in order to achieve an output voltage which is shown on the lower part. The red curve is the loading current on the inductor which we have here. So depending on the duty cycle of the switch 1 and switch 2, you can achieve a higher or a lower loading current, and therefore you can regulate the output voltage just by changing the duty cycle of the switching. So it's some kind of pulse width modulation. At this slide we have listed the design challenges. So based on the requirement and the taken measures, we will see a bunch of challenges which have to be solved. So to achieve a higher efficiency, you can select a different topology. You can also change your switching components from standard silicon based to wide bandgap devices, so silicon carbide, gallium nitride, are on their way to the commercial market. You also can increase the switching frequency, but these measures can also lead to certain challenges. So higher switching frequency is very often responsible for higher EMC. This slide shows how the efficiency improvement through the change from silicon-based switches to silicon carbide-based switches could affect the EMC. So the first thing is the switching signal, which we have here in blue. It had a 1 microsecond rise time, which is a typical rise time for silicon-based switches, and the resulting spectrum is on the bottom here. If we now change to a silicon carbide based switch which has a higher rise time, and we're using the same switching frequency in general, we immediately can see how the spectrum changes, and it reaches also higher frequencies which then could be emitted to the outside. If we now also think about the possibility that silicon carbide based switches can have a higher switching frequency, then also the spectrum would be extended to even higher frequencies, and then we are coming into a region where EMC problem really could be a problem. Let's have a look at the question if simulation can make testing obsolete. At the current stage, I think it is not yet possible, because the simulation is based on the modeling and also on the available data which we feed into the system. And depending on this, the difference to the real world measurement might be different, or is still different. Let's have a look at the component data which is available. If you look in the data sheets, most of the time you won't find exactly what you need for your use case. So for passive exactly, ESR, ESL, AC resistance is not always given, or not always given in the right frequency which you need. With different currents you have different inductance values. Ceramic capacitors have a dependency on the DC bias, so it depends in which point you use it, which DC bias point. So there is still a lot of need to do the tests and at least measure the components by yourself first. Overall, I would say for the testing we have two different parts of testing. I specify the left part here as the must-have testing, which is something like the compliance measurements to be able to get the CE mark, and also the performance and reliability measurements regarding stability. So if the product isn't working properly, you might have difficulties to sell it. You will have difficulties to sell it. On the performance testing, this is really then something which determines how good is it, how good is the efficiency, how fast is the response, and so on. Let's have a look at the measurements. The stability is the first one I want to have a look at it, because I already mentioned it several times before. That is a very important part in the power supply design. The most common measurements around this is the Bode plot. The Bode plot is a measurement which plots gain and phase over frequency. So what we have here on the right side is we have a source, an isolated 25 MHz function generator with isolated output, which means you can directly connect it to your device under test into the feedback loop and inject the signal, which is changed then over frequency. And then you do two measurements. First is the reference measurements on the input side, and the output side is the second part of the measurement. And then you plot the ratio of the gain change from input to output and also the phase change from input to output. And then you get a plot like you have it here on the left side. From this plot you can find out at the 0 dB, so means amplifying of 1, how far is the margin from 180 degrees. And there is a rule of thumb that you have to have minimum 45 degrees difference in phase. That's the phase margin, and from this point on it can be considered as stable. The Bode plot, of course, can also be used for measuring the components I mentioned in the slide before, or you can also use it for filter measurements and optimizing filters. So let's now have a look at the load step response measurement. So here on the right side we have the electronic load, which is capable of switch between two states of current to pull it from the device, the power supply and the oscilloscope for analyzing. Why do we measure load step response? First of all, it's important for us to know how fast the regulation works and how deep the voltage drop is, or how high the overshoot is in this case. And of course, if we have ringing, which shows us that we have an unstable or at least a not optimized setup. Here on the two pictures, the lower part is an optimized design, and on the upper part we have a not optimized design. What you can see here at the ringing, when we switch the current, pull the current and release it again. Having a look into the switching stage inside, first of all, it is most of the times a little bit more difficult to contact the right points for the measurement, but in general this measurement gives us a little bit more insight and helps us also to optimize the performance, because we can determine the dead time between the switching cycles and optimize everything in this case. And what we see here in this case, we have here an ringing again, which comes from the LCR or LC resonance here, which comes from the inherent capacity between drain and source, and also, if the design is not well done, the inductivity from the trace. So this gives a resonance, and related to the values we have, we can see ringing frequencies up to bigger 200 megahertz. And this of course is probably an issue if you're looking at EMC later on. Last but not least, we have here an overview about the power analysis measurement. We have divided it into input stage, switching stage and output stage. Current harmonics here is important because there's a standard which we have to comply. So this is a special position. At the switching part, the switching loss is also an interesting measurement. And at the output side, very important, transient response, we just talked about it. And also output ripple and efficiency is the main task. The last slide for today gives you an overview about all the products we're offering. We have oscilloscopes, spectrum analyzers for EMI pre-compliance testing, power supplies, DC loads, multimeters. Thanks for your attention and have a good day.